Hi everyone, I am Balamurali Murugesan, and my research interests are mainly focused on developing reliable deep learning models. And today I'll be presenting my ECCV work on robust calibration of large vision language adapters. And Ismail and Jose are my supervisors, and I will also extend my thanks to my wonderful co-author Julio. Yeah, before going into calibration, let's get into what is this vision language models, and I'll give a brief about different types of methods, and I'll introduce calibration, and then we'll discuss about our solution and respective results. So the first is recently we have this model called CLIP, which is called contrastive language image pre-training. The idea behind this is, assume you have an image encoder and you have an input image to that, and you get a image representation, and assume that you have n possible text given to the text encoder and get n possible representation. You're just doing a correlation between that particular image and the respective text. You can treat it as a classification problem. For example, when you want to do a pre-training with the contrastive setup, you can give n possible images and n possible text. As you can see, all we want is we want to maximize the distance between the image representation and the text representation for that particular pair. So that's why if you see in the diagonal, we want that to be maximized, and the other one you want to be minimized. The correlation between the respective text and image has to be maximized. This is how the CLIP model has been trained. So because of this kind of training, the beauty is when you want to pose it as a classification problem, what happens is you assume that there are n possible classes, like here plane, car, dog, and bird. You just give it to the text encoder and get n possible representation. Now, having just an image and then doing a correlation with all the possible representation will give you a score. The one with the maximum will be your prediction. So this way, the CLIP models have been now used for zero shot prediction without even training to your data set. You can just directly go and check whether if you have a good amount of text data and then images. And this is and importantly, there is another paradigm called few shot learning. Even though the CLIP models have very good zero shot performances, but there is always a possibility that you want to adapt the CLIP models to your particular task. So for that, the general paradigm is like this. So assume you have a support set and query set where the task is you have k classes, and then for each class you have n samples. So during training, if you provide different possible support sets and query set, and you can just go to the inference time and provide just a support set with n, let's say equal to 3 and k equal to 2, when from a different distribution, you can still make it work. So recently, the CLIP model which we discussed earlier, they have been adapted using this few shot setup. And some of the protocols at which you can achieve this, we will discuss it now. So the first is, I'm calling it here as adapters. And there are different types of different ways we can use these adapters. In this paper now, I will be discussing about tip adapter. Just I'll give a brief on this. So assume that you have few shot images with the visual encoder, so you get the representations. And now you have labels for that, few shot labels, and you get the label information here with the one not data. Okay. And now it's possible to actually use them and then form a deep learning network with just filling that values into the weights. So what happens is you now have an information about the few shot data during the training time, and now during the inference you just give the image here and then you get the image representation, and these are the possible text images. Okay, so once you do this, we have two possibilities. One is directly as a zero shot inference, you get some information, and also from the few shot information, few shot weights, you also get one result. So you can do a linear combination of that, and then you can have a final prediction. So this is how tip adapter works on few shot data. So other important thing to note here is adapters are general. Instead of working on the prompts or instead of working before the results, it works after the representation. So once the representations are obtained from the images, we apply some kind of post processing to get to the classification layer. Keep that in mind. And now this is another type of way we can approach the few shot adaptation to clip, and that's called prompt learning. The idea behind this is, like, instead of adapting the features here, let's say after the text encoder and image encoder, you have the possibility of updating the prompt before even updating the representation. So for example, here, let's say you give a photo of aeroplane to the text encoder and an image of this image. So now what you do is you use a few shot setup and try to maximize the correlation with this being learnable. So that way, instead of updating the parameters after the text encoder, you are actually updating the input. So that's called prompt learning. One of the famous techniques is co-op. So like that, there are techniques like co-op, KG co-op. And similarly, for in adapters, apart from tip adapters, you also have clip adapters, you also have task arrays. So I will show them in my comparison. And finally, one of the important methods in this is not exactly few shot. Here it's more practical setting where you only have single image and you don't have a ground truth. You want to do a classification with that. Okay, so now you take an image and do an augmented n type of augmentation. You have a single prompt. So now what you do is, we don't have the label, so we are just using unsupervised entropy maximization here. Okay, so once we do this, what happens? You are trying to update the prompt here, but without having the label information. Okay, that way you can just do this directly in the inference time. Okay, these are all the three types of techniques which we can use to adapt clip models. And now let's discuss about model calibration. So here the first row, the top row is the graph of cross entropy loss, and the second row is an example of how the calibrated model will look like. Okay, let me explain the figure now. So the x-axis is nothing but confidence and y-axis is nothing but accuracy. So the thing to note here is, in cross entropy, when the number of epochs are increasing, even after achieving the required confidence, required accuracy, for here, for example, if you consider here and here, it's almost achieved the desired accuracy. But what happens is, because of the design of cross entropy, the confidence still it tries to reduce. So you can see that confidence is becoming almost reaching 1. This shows that cross entropy always provides overconfident result. Okay, but now when you look at the bottom one, you can see that after achieving the desired accuracy, the confidence stays there. So it doesn't become overconfident. So this is a typical behavior one want in a reliable model, and the way to achieve it is model calibration. Now the thing is, we discussed about this adapter prompt learning and test time prompt learning. All these methods have this problem. When you do a few shot learning adaptation, or when you adapt it to your task, what happens is your performance, the discriminative performance or the classification performance actually increases, but the calibration is significantly degraded. So it is the figure below is a similar one as that of the one which I showed earlier. So you have confidence in the x-axis and accuracy in the y-axis. And EC is a metric to measure calibration. So when you note here, and before that, yeah, so I have considered ImageNet v2 dataset, and from each of the methods discussed, I have taken co-op, clip adapter, adapters, and TPT from prompt learning, test time prompt learning. So in each of the cases, you can see that once the adaptation is done, your EC actually increases, which means its calibration is becoming worsened. So one thing to note here is the zero shot performance, the calibration of zero shot is less than the adapted ones, which means when the model is adapted, you are losing the calibration. Okay, keep that in mind because we will be using this information to propose our solution. So here the takeaway is the zero shot models are better calibrated than the models adapted in few shot setting. And this is another method called logit norm. Logit norm noticed that I showed you the figure, right, where when you are doing the training across epochs, your confidence is becoming overconfident, which means the logit is keep on increasing. The logit value is keep on increasing. And in this work, they noted that reducing the overconfidence is due to the increase in logit norm. So they noticed that, and then they proposed a loss function wherein they restrict the logit norm becoming too high. So that was their proposal, and it was mainly studied for OOD deduction. So here you can see the comparison between cross entropy and logit norm. In the left one, you can see that both for in distribution data and out of distribution data, there is a high confidence score, which we don't want. In logit norm, you can see that in distribution, the confidence is very high, and in outer distribution, it's very uncertain. By that, I mean like it's uniform, right? The confidence scores are uniform, which means it's very uncertain. So which is a good thing to predict the outer distribution samples. And this is another demonstrative figure where you can see that this brown color, right, that represents the OOD distribution. So with the logit norm loss, they show that you can actually get the data, whereas in cross entropy it is difficult to discriminate the OOD samples. Having said that, when we were conducting some study on OOD generalization, we found that the problem of miscalibration is not due to logit norm, but due to the range of logits. What do I mean by that? So I have considered a setup here. From each of the methods discussed, I have taken clip adapter, co-op, and TPT, and I have compared it with zero shot. Okay, that the bottom one is logit range and the top one is logit norm. You can see that with the increase in logit norm, the ECE doesn't seem to increase. And when you see here, when there is an increase in logit range, the ECE seem to increase, which means when there is an increase in logit range, the models are becoming miscalibrated. Whereas the logit norm doesn't actually have a direct correlation with calibration error. So that was our key observation. And based on this, we propose our solutions. And you can also notice that zero shot is better calibrated compared to the adapted ones. Yeah, so now let's get into the specifics of the methodology. So assume that you have an image encoder in clip with denoted by data and the text encoder denoted by phi. So you have a vision embedding which is denoted by Z, and the text outputs, the weights, we call it as weights. So that will be WK. So now let's assume there are K class problem, and for each of the classes, assume that there are ensemble prompts, and then you have a class zero shot prototype which is denoted by TK. So this is the final representation. TK is the final representation and Z is the final representation from image side. So now when you do this softmax kind of setup, you can actually take the argmax of this and get your intended prediction. And here the tau is the temperature hyperparameter, which is to control the scale of the logits. And few more things that is the one which you discuss now is for clip zero shot, right? We need to adapt it to our novel task. So here you can see for co-op, you are actually learning the TK, and for adapter methods, you are learning the new parameters, right? You are introducing a transformation after the visual and text embedding. So that will be our new parameter, which is denoted by here data. And then finally, the test time prompt learning. Here we can either update the prompts or you can also update the post-processing step. And this is just a proof to show that why logit range increase actually corresponds to miscalibration, and the logit norm doesn't. So you can just take these two scenarios. You can see that when you just add a constant A, it actually increases the logit norm. but the confidence still remains the same. When you apply to softmax, you can still get the same confidence for that particular prediction. But when in the second proposition, you can see that when you increase the range, which is like I'm just multiplying it by a factor, when you do that, your confidence score will also be high because the logit is stretched. Okay, so that's what we mainly wanted to convey here. And coming to our solution, so having observed all this, what we can come up with is the following. So you are trying to adapt to a particular task, and then in the process the logit range is becoming higher, but we noticed that the zero shot logit range is better calibrated. Zero shot is better calibrated than this few shot. So what we were proposed is, let's take the logits and try to constrain it within the zero shot range. So what do I mean by that? So you take a sample and get the zero shot prediction. Let's say logit LZS min and LZS max. So now when you do a few shot, the entropy, the cross entropy has to be designed in such a way that the logits are never higher than the zero shot max logits and never lower than zero shot ZS min. This way we are ensuring that the logit doesn't explode or logit doesn't allow the confidence to be extremely high. So this is our proposal. And how do we incorporate this as a loss function, as a normalization? We'll see it here. The first one is zero shot normalization during training. We call it as ZS norm. So what we do here is, we know that cross entropy is defined by the following term, y, log, and softmax. So what we do is, before applying the softmax, we renormalize the logits using the following equation. You can see that this is as simple as min-max normalization. You are taking the maximum and minimum of the logits during training and then renormalizing it back to the range of ZS max and ZS min. And once that process is done, you are passing it to the softmax equation. So this way, during training itself, you are ensuring that the logits doesn't cross the zero shot boundaries. And we have also proposed one more way to incorporate this, and that could be done by, instead of normalizing the logits, we can also restrict the logits separately as a regularizer term. How do we do that? So here we have a cross entropy term, but separately we have two terms and both are ReLU based. Here we are having a ReLU to constrain the logits within the maximum logit of zero shot and minimum logits of zero shot. And the thing is, we have a parameter called lambda to control it, but in typical regularization systems, lambda could be found, and we chose a value of 0.1, and that seemed to work in most cases. And if you need to have more importance to the regularizer, you can even increase the lambda accordingly. And finally, one more solution is sample adaptive logit scaling. The two solutions which we discussed earlier are mainly focused on training mode. So you are trying to normalize the logits, or you're trying to constrain the logits during training. But what if you don't have access to the training thing? You just have the model, and during the inference time, you want to do the rescaling part. So what we propose is an unsupervised sample-wise temperature scaling. So here you don't need additional, generally when you use temperature scaling, you need additional data to find the temperature value. Here we don't need any additional samples. We give just one sample and then get the zero shot prediction, and we give our whatever models you have, and then you get that prediction. So what you do is you take that prediction and try to renormalize it based on the range of zero shot. So this way you can just do this during the inference time itself. So we have proposed two training based loss functions, and then during inference also you could do this logit scaling. And how do we evaluate our method? So we used a 16 shot training support set, which is ImageNet, and out of distribution test data are ImageNet V2, ImageNet Sketch, and these are different out of the distribution data for ImageNet, and you have ImageNet adversarial, and then you have ImageNet R. And we also have something called fine-grained task, where we have something like Caltech, Oxford sets, and this is a very standard to evaluate out of distribution data sets. And regarding the evaluation metrics, we are using classification accuracy and then expected calibration error. And expected calibration is nothing but the difference between the accuracy and confidence. So first we'll see the results of few shot adapters. So we have clip adapter, tip adapter, and then task res. So the average OOD is nothing but the average of image v2, image sketch, all the results average together, and that's done for accuracy and expected calibration error. So we have shown it for three methods, all of our three methods, and we can see that uh, compared to the calibration score of the original few shot, like 15.45, it's reduced to 8.95, and 19.04 to 8.13. So this happens for both the left one is for ResNet, and the right one is with the transformer models. So I can see irrespective of that model choices, we are still able to provide the expected improvements in calibration. An important thing to notice, even our method is able to increase the discriminative performance, which is really a good thing. And these are some of the results with few shot prompt learning. So here we have considered co-op, co-op, and prograd in ResNet. And for V80, we have considered co-op, co-op, and Maple. So as discussed in the previous slide, here also you can see that from 7.69, you can see 6.15. That's a good improvement. And there is also an improvement in terms of discriminative performance. And yeah, and seems to be the method seems to be consistent across. We have test time prompt tuning, where we have considered two methods. One is TPT and another is CTPT. So in all these methods, we have incorporated our loss functions, ZS num and penalty, and this is like temperature scaling in the inference. So this average is nothing but the average of all the results in the right side. You can see overall we are getting improved accuracy as well as improved calibration performance. And these are some of the reliability plots, where you can see that this is co-op, and these are two ImageNet V2 and ImageNet adversarial. So you can see that with the introduction of objective functions and post temperature scaling, we are consistently seeing decrease in calibration error, which is the expected one. And if you look at the graphs especially in the diagonal, you can see that the width is big, the height of the plot is very high in co-op, and when you incorporate our methods, that size reduces, which means the accuracy and the confidence are better correlated compared to the adapted ones. And similar things could be observed in the adapters. Like you can see, especially for SALs, you can see that it's drastically does reduced the height of the error bars. Yeah, similarly, we have also done for TPT. You can see here, compare clip adapter this row and this row. You can see that there is a drastic decrease. And one more thing which we also studied in our paper is, okay, so we are using directly the zero shot scale to normalize. What if you want to scale it below, like by an half, by a quarter of zero shot? The thing is, you can do that, but if you try to do it more, the predictions become meaningless, because you are trying to push it to a uniform distribution, which is not a good thing, because your accuracy can decrease. So that's why I would say this is an hyperparameter. If you want, you can tune it a bit. I think, having the direct range of zero shot will be good. And if you want, you can try it with values like 0.9 or 90% or 80% of zero shot, and see which one works better. And this is to just show that when we incorporated our method, so the logit range, there is a decrease in logit range after trying our method. So this was the initial case, and once we incorporated the logit trend decreases, so calibration error also decreased. That's not the case with logit norm. So you can see that the logit norm was always increasing. To conclude, we show that the underlying cause of miscalibration in adaptation is with increase in logit range, and we provide two solutions: normalization and penalty during training, and an unsupervised scaling during inference. Solutions reduce miscalibration error in popular OOD classification benchmarks, and it's across adapters, prompt learning, and test-time prompt tuning methods with different architectures. And you can also find the code in GitHub, and this is the link. Yeah, thanks for listening to my talk.